and welcome to the May edition of Trainee Talks. For those of you who are new, Trainee Talks is a series of research talks delivered by software engineering graduate students in the CREATE SE4AI program. Everyone is receiving specialized training in the technical and social aspects of AI-based software systems. And my name is Lori Akiyama. I'm the program coordinator here at Concordia, and I'll be moderating the webinar today. Today, I am very excited to introduce two amazing CREATE trainees who are nearing the end of their master's journey and will be graduating soon. So I'm excited that they're graduating, but really sorry to see them go because they've both been amazing contributors to our program here. And I'll give a brief introduction to each of them and let them take it away. So first we have Chaima Jaziri. Chaima is an MASc candidate in software engineering at Concordia University under the supervision of Professor Imad Shihab, and she is of course part of the CREATE program. Chaima holds a Bachelor of Engineering in Applied Computer Science from the National Engineering School of Sousse. Her research focuses on agentic AI systems and the application of large language models to automate complex software engineering workflows. She has over 3 years of experience building AI systems, including model fine-tuning, evaluation, and deployment. Chaima has worked as an AI engineer at White Cape Technologies, Ericsson, and Aduna Global, where she developed traditional ML systems before transitioning to building multi-agent solutions and LLM pipelines for real-world applications. And today, Chaima will be presenting her work titled Co-DynaDev, a dynamic multi-agent assistant for automated software development. And next, we have Khandaker Rifah Tasnia, who is a software engineering master's student at Concordia University under the supervision of Professor Jinqi Yang. Rifah is researching AI-assisted classification of suppressed static analysis warnings. She has professional experience as a database engineer at Therap Services and as a data analytics intern at ICVIA, where she worked with healthcare and pharmaceutical data modeling and reporting, data visualization, and ETL pipeline development. Her interests include applying data-driven and AI-based approaches to improve software quality, decision-making, and real-world analytics systems. Today, Rifah will be sharing her work on KAS-C, an LLM-based Knowledge Augmented Framework for classifying static analysis warning suppressions. So each trainee will speak for around 20 minutes, then we'll open up the floor to Q&A. And the webinar is being recorded as usual and will be available to view on our CREATE website and also on our YouTube channel. So with that, I'd like to turn things over to Chaima.
Thank you, Laurie. Thank you for a great presentation. Can everyone hear me? Okay, perfect. So good morning, everyone. My name is Chaima Jaziri, and today I will be presenting my thesis research titled Co-DynaDev, a dynamic multi-agent assistant for automated software development. This work was conducted under the supervision of Dr. Imad Shihab and co-supervised by Dr. Darwin Ahmed from UCAC. This presentation is organized into 6 sections. I begin with the context and problem statements, followed by a review of related work and our research questions. I then describe the Co-DynaDev system and its methodology. After that, I present the result, discuss their implications, and conclude with limitation and directions for future work. So the goal has always been the same, is to describe what you want and get a working software back. Developers still, until today, spend most of their time on predictable, repetitive work. The vision here is to automate all of that so they can focus on what only they can do, such as solving the actual hard problems and understanding the user real need, building things that didn't exist before. So automations isn't about replacing developer, but it's about letting them work on what only they can do. The first wave was of these automations produced focused tools with well-defined scope. We had EvoSuits and Randop that produced unit tests at scale with high coverage, GenProg and Simfix that generated patches directly from failing test suits, and CI/CD pipelines that eliminated manual builds and deployments bottlenecks. So the critical limitation shared by all those tools is that they are not only scoped by designs, and none of them can simultaneously reasons about the requirements, the architecture, and implementations across a full project. Then LLM arrived, and for our first times, we have a model that can resonate about the entire development workflow and eventually provide a complete task and problems. But the question is, are those generated codes and files correct? Is it usable? Is it maintainable? Most of the time, it's not, and it highlights the fact that LLMs only chat. They have no hands in the environments, and that leads that the developer becomes the bridge between the chat and terminal, and every switch bleeds in the effort, time, and context. Single agents gave LLMs hands, which is the ability to write files and documents, and this was a meaningful step forward, but one pair of hands is not enough, as single agents still fail on real projects, and it can be due to the context drift, the lack of a persistent memory across sessions, and frequently hallucinated dependency. So these observations leads naturally to the idea of adding more agents and maybe simulating the software team. However, this approach as well introduced their own failure modes. The first one is rigid role hierarchies. That fixed predefined role in multi-agent system became brittle as project scope evolves and cannot adapt to shifting requirements. This also was built to support isolated tasks, and fixed role cannot adapt to change. Also, adding more agents is not a solution, as it has been showing that the more agent you add, the more they talk and not build. We have a streaking stat from Asian Taxo that showed that 72% of tokens in MetaGPT system developments tasks go to verification overhead and not the code generation. The second failure mode is what I call distributed amnesia. So in a pipeline from agent A to agent B to agent C, the context is lost at each boundary, and this fragmentation means that a fix in one part regress work done in another part. The third failure mode is missing execution grounding. Agent agreed that the code is correct without even running it, and the consequence of this is that we have a missing dependency, incorrect configurations, and runtime exceptions that go undetected until a human being executes the output. The fourth and final failure mode is that the human is removed from the loop. We have multi-agent system that runs start to finish with no way to capture evolving intent. And the output sometimes is often misaligned, not because the agent failed, but because the goal have shifted and the system have no mechanism to adapt. Also, the lack of control can cause agent to take unsafe and irreversible actions, as what happened with Replit agents that deleted a prod database. So this leads to our problem statement that automating software development end-to-end requires an agentic system that can plan, implement, and validate across evolving multi-file project, while also retaining context, adaptations to execution signal, and remaining aligned with the user intent. So with the problem is being clarified, let me briefly situate this work in the existing literature. The landscape of related work can be organized into three waves. The first one produced foundation LLM code generator like Codex and AlphaCode. They demonstrate strong function level synthesis, but were limited to single function scope. The second wave produced IGE assistant like GitHub Copilot. They have improved the human AI collaborations with real-time suggestions, but they remain assistive and not autonomous. And the third wave produced multi-agent system which handled more complex workflow through the role-based task distributions. However, those systems all share the limitations I have described. This thesis proposed Co-DynaDev, a context-aware assistant that built on a dynamic two-agent architecture. So rather than assigning fixed role, Co-DynaDev has meta agents and a worker agents whose responsibility shift based on the current project state, and they collaborate through hybrid memory, sandbox executions, and structured human checkpoint. We organized our evaluation around three research questions. First one asked about end-to-end effectiveness. How effectively can Co-DynaDev automatically turn high-level prompt into functional project? Second RQ asked about scalability. How scalable is Co-DynaDev as project complexity increases? And final RQ asked about failure modes and robustness. What are the main failure scenarios faced by Co-DynaDev and which solution can improve its effectiveness? So I now describe the Co-DynaDev system. This diagram provides an overview of the full system. The user interacts with the meta agents and send a request. The meta agent proposes a plan and seek human approval at human validation checkpoints 1. Following the approval, the meta agent decomposes the task and delegate the subtasks to the worker agent. The worker agent executes in an isolated Docker sandbox, and before running any potentially destructive command, a second human checkpoint is triggered. Both agents continuously update a shared context manager that store the user preference and short and long memory. So the system is a continuous feedback loop and not a linear pipeline. The first key architectural innovation is the dynamic two-agent design. The meta agent is responsible for thinking, planning, and control, while the worker agent is the execution engine. Critically, the responsibility shifts following a dynamic orchestration policy. So at each iteration, the meta agent reads 5 signals: the current requirements, the workspace state, the execution logs, the test result, and the memory, and then decide what to do next and how own it. So this is fundamentally different from the prior work and system because previously the coder always code where the tester always tests, but here the system adapts continuously to what actually happened. Memory is what prevents the distributed amnesia problems through 3 layers. First is the short-term memory that holds the current sessions. It stored the recent dialog, the file diff, the latest log. The second is the long-term memory that persists across sessions and is stored architecture decision, resolve dependency, conflicts, recurrency fixes. And finally, the user preference that is persistent as well and is stored the preferred frameworks and coding conventions. So this is what allows the system to maintain coherence across long tasks without overload, drift, or repeated clarification. The sandbox solved the missing grounding problem. Every artifact run in a fresh Docker container, which is isolated, reproducible, and environment consist, where we build, run, and test, all happen inside the sandbox, and we have the logs and the errors that stream back in the real time. So here the agent don't assume that the code works, they know because they have run it. Co-DynaDev as well keep the human in control through a 3-panel agent computer interface. The first one is the chat panel that provide the human data loop for dialogue. The IDE-like editor that gives a live repository view of all the generated files. And finally, the execution terminal, the real-time runtime view from the sandbox. So here, the user can observe and interact optionally with the system, but we have 2 mandatory human checkpoints that we enforce. The first one is that it happened after the user submits a request and the meta agent proposes a plan that contains the tech stack, the architecture, and the next steps. And here the system pauses. The user can approve, revise, or reject before any code is written. The second checkpoints happen before executing any ghostly commands, such as installing dependency or running tests or building Docker images. And here the system summarizes the intended actions, poses, and the user approve or cancel. So those are not optional, and no execution happen without passing both checkpoints. For evaluations, we designed a three-level benchmark suite that increases in complexity along two dimensions, the project scope and the engineering depth. So level one is software dev benchmark that contain 10 small self-contained programming tasks, such as mini games, and they were publicly available from previous work. And then we constructed 10 additional tasks in the same style. And because software dev does not provide ground truth tests, we constructed a shared test of unit and accepted test as well. Level 2 is DevBench benchmark that contain 10 medium scale projects with full design documentations. And level 3 is code project eval that contain 18 large realistic repositories. We have compared Co-DynaDev against four state-of-the-art baselines, the MetaGPT, ChatDev, CodeS, and Project Gen. Our evaluations covered 6 complementary dimensions, the functional correctness, the project structure, the test quality, the design quality, the efficiency and cost, and the static quality. I now present the results for each of our RQs. First RQ, we asked it how effectively can Co-DynaDev automatically turn high-level prompts into functional projects, and we evaluated on software dev against ChatDev and MetaGPT. Here we have rerun it, all those systems under identical conditions, and we have measured across 3 dimensions the project structure, the functional correctness, and the efficiency. So starting with the project structure, Co-DynaDev achieved the highest executability score, which is 3.9 out of 4. It generates about 4.5 files per project, with roughly 87.5 lines of code per file. Our key finding from here is that there is a sweet spot between under specifications and over fragmentations, while ChatDev underbuilds with while MetaGPT over fragments. We found that Co-DynaDev meta agents actively shapes the structure toward what is runnable and not just what is complete. In terms of the functional correctness, Co-DynaDev achieved a 97.5% unit test pass rate and 100% acceptance pass rate. Those compare favorably to MetaGPT's 41% and 57.5%, and ChatDev at 29.2% and 7.1% respectively. For the average code coverage, it scores 90.6%, which is more than double the coverage achieved by either baselines. And on efficiency, Co-DynaDev completes tasks in approximately 3 to 4 times faster. And in token conceptions, it consumes 41.7% lower than ChatDev and 64% lower than MetaGPT. Two key findings from this is that the execution grounding is what makes the correctness possible, not just the prompt quality, and the speed and correctness are not intentions when orchestrations is efficient. Moving to RQ2 results, we asked how scalable is Co-DynaDev as project complexity increase. So the concern with any system that works well on simple tasks is whether it collapses at scale. We have evaluated on DevBench and Code Project Eval and compared against all the 4 baselines. We measured 4 dimensions base here, the design quality, the environment setup reliability, the functional correctness, and the static code quality. On design quality, Co-DynaDev maintains consistently strong design across all the 3 complexity level, and the total design score stay above 74 out of 100 score at every level by an LLM as a judge. On environment setup, Co-DynaDev achieved 100% environment success rate across all the benchmarks and identified core library and infers the compatible version constraint in at most 3 Docker iterations. So moving to the functional correctness and at higher complexity level, Co-DynaDev scores 78 out of 124 tests at level 2, and the next best baselines pass only 47. And when for level 3, Co-DynaDev passes 724 out of 3,348 tested, when the next best passed only 310. The key finding here is that the complexity is where architectural choices are tested. Moving to the static code quality, the linked error density is 9.48 errors per 1,000 lines compared to 7.4 in the ground truth, and approximately 2/3 of generated files are completely lint clean. The mean cyclomatic complex is 5.1 versus 4.7 in ground truth, and finally, the high complexity functions are 12.3% versus 9.6 in the ground truth. So the finding here is that the human written repository retain a small quality edges, but Co-DynaDev does not systematically introduce worse static quality. Finally, on test quality, the Co-DynaDev generated tests that catch 79% of the injected mutant compared to human written tests that catch 88%. And notably, the freaky rate of Co-DynaDev generated tests is 0 compared to 0.04 for human written tests. So we can say that the generated tests are more stable. The key finding is that generated tests are not just self-validations, scaffolding. Passing to the statement coverage, we have scored 91.2%. For a branch coverage, it reached 85.4%, and the exceptions coverage reached 76.1%, which is the lowest dimensions and points directly to one of our failure modes that we examined in RQ3. So in RQ3, we asked it what are the main failure scenarios faced by Co-DynaDev and which solution can improve its effectiveness. Even with strong aggregate results, some projects still fails, and understanding why matters as much as measuring the success. We took two steps approach in this: a post-mortem analysis when we manually inspected all the failing execution traces, followed by a mitigation experiment where we introduced the solutions and measured its effectiveness. So we have identified 6 failure modes. First one is code narrations interleaving at 23%. It's where output mixes the natural language or markdowns with the code. F2 is evaluation contracts mismatches at 90%. Here, the semantic correctness or the modernized code failed the rigid benchmark harness, and it can be due to the naming or the different API versions. F3 is the editing fatigue at 13%. Edits become increasingly generic or non-specific across iterations. F4 is for the Asian reasoning loops and non-conversions retries at 15%. The system revisits the same code segmented or failure repeatedly without making progress. F5 is for the content filter interruptions at 7%. The filter flag legal boilerplates or scaffolding tests at inappropriate. And F6 is for the persistent exceptions under coverage at 23%. Exception path coverage average only 76%. And we found that the agents under explore edge cases and invalid input, and they prioritize happy path logics. So the most important observations is that almost half of failures came from F1 and F2, that they are surface level artifacts that we have addressed, that are addressable with lightweight early validations. And here we are introducing a first solution, which is integrating an abstract system, a syntax tree validation layer as a mandatory. So every code or every artifact that is produced by the worker agents must successfully parse as a valid AST before it's committed to the memory. And for our result at level 3, the passed taste increases from 78 to 115, which is a 29% improvement. At level 3, the passed taste increased from 724 to 1,151, which is a 30% improvement. So An overall key finding from this is that you do not need a better model to fix most failure. You need a better solution designs, and the reliability overhead solutions be measured, not assumed. Finally, as a key findings from overall, first one is that the execution grounding is not negotiable. Prior system agreed that the code is correct without running it, but Co-DynaDev runs everything, and that signal decision it explained most of the correctness. F2 is that the context infrastructure is not a feature. And finally, adaptability and agility, both specializations at scale. I will pass to the discussion for the sake of the timing. We have run different more experiments to see the sensitivity to model choices and the decoding templates. So on model choices, the Co-DynaDev perform consistently across GPT-4o, Claude 3.7, and open source model Quail 3 next 70 billion, and the design quality stays above 70 for all three with small variation. For the decoding template that we lowered from 1 to 0.5, it improved the pass rates and reduced exchange, token, runtime, and costs. Our implication for practitioner is that small, well-orchestrated teams works best. The environment and execution are a first class. Practical safeguards as essentials, as we saw in F5 and F6. And the bottom line is that the robust agentic software engineer system came from how we structure interactions, validation, and memory, and not just more models or agents. Finally, we have looked into how this system can be used in the industry. We conducted a small-scale practitioner study uh, within my internship with three industry professionals, and we have collected their opinion about the component of hybrid memory, that this absence of this component result in the reintroductions and of previous resolved bugs and the loss of high-level design decisions. For the sandbox execution, the lack of this delayed the error detections and led to inefficient debugging process. And for the human of the loop checkpoints, the absence of that necessitate higher level of rework later in the development cycle. So Co-DynaDev showed strong improvements, but there are still important limitations. First, the evaluation is not fully controlled, since the real execution introduced variability. Second is that the correctness is approximate through the test, which is cannot capture all the edge cases. And third, that the generations is limited as experiment focused mainly on Python-based benchmark. For the future research directions, we need strong validation layer beyond syntax, including semantic and contract word checks. Second, standardizes benchmarks that reflect the full software lifecycle. And finally, more scalable and reliable agent architecture toward general purpose autonomous system. This work is currently under review at the ASM Transactions and Software Engineering and Methodology, which is TOSAM. And thank you, everyone. I think I took a bit more time than.
Thank you, Chaima. That was amazing. I just wanted to mention that this research forms Chaima's master's defense, and I had the pleasure of attending her thesis defense last week, and she received an outstanding. So we're very proud of Chaima and all the hard work that she put into this project.
Thank you,
Yes,
Lori.
applause all around. Does anyone have any quick questions? Or maybe what I'll suggest is that we move on to Rifah's presentation, and then we can have the questions at the end. I think that might work better because, yeah, we're a little bit over. So if you have any questions for Chaima, please save them until the end. And now I'd like to invite Rifah to please share your screen and go ahead with your presentation.
Yeah. Oh, can you see my screen?
Yes.
Okay. Mm. Okay, hello everyone. Today I will present our work, KAS-C, a knowledge augmented LLM-based approach for automatically assessing the static analysis warning suppressions. And in this work, we focus on suppressed spot bugs warnings in Java projects and study whether LLMs can help distinguish between justified suppressions and suppressions that may hide real technical data. So, static analysis tools are widely used to detect bugs. It also used for detecting security vulnerabilities and code quality issues early in the development phase without executing the source code. However, these static analysis tools are not really perfect. They can report false positives, or they may also produce warnings that are technically valid but not actionable in specific project context. So to deal with this warning, developers often suppress warnings using suppression annotations, such as for Java, for spot bugs in Java, developers use suppress FB warnings. And the problem is that um, suppression is not always harmless. While some suppressions are justified, some suppressions may hide real defects, which can contribute to technical debts. The key challenge is that suppression annotation alone does not tell us why the developer suppressed the warnings, and the same suppression could represent a false positive and actionable design decision or a real fixable defect. So understanding this requires reasoning about the warning type, the surrounding code, and uh, the surrounding code, the developer's comments, commit messages, and also sometimes the evolution of the suppression. So here, let's have a look at the life cycle of suppression in Codebase. So after a static warning is detected, developers sometimes fix it, sometimes ignore, or sometimes just suppress it. So even after ignoring, sometimes developer later goes and suppress the same warning. And while a suppression is newly introduced, sometimes it remains present in the code base, and sometimes it's removed. Developers sometimes like fix the warning and then remove the suppressions, and sometimes just remove it without fixing it, or because the associated code is completely removed. That's why the suppression is removed along with the code. So for our study, we are focusing on the warnings that are suppressed by the developers. Here is an example. Here is an example. The developer initially suppressed a DM exit warning here, but later developer removed the suppression and also fixed the underlying issue of the warning. They removed the system.exit0 calls, which fixed the warning, and so the suppression annotation and was removed. So based on our analysis and prior studies, we have found out that we can categorize these suppressions into three categories based on their maintenance impact and the developer's intent. So first one is the false positive, where analyzer incorrectly reports a warning and the code does not really contact a defect. And the second one is unactionable. Here the warning is valid, but the developer intentionally accepts the warning because of design decisions. There can be external guarantees like third-party involvement or third-party library codes. And sometimes there are some testing codes or not, and some codes which are not used in production. So developer ignores warnings and accept those cases. And the thirdly is technical debt, where the warning is valid and it indicates are real defects that should be fixed, but instead developers suppress them. So, here is an example of the false positive case. Here, the code actually checks for class ownership. Class ownership, if class ownership is null or not, and this and here the reported warning NP null on some path is does not correspond to a real defect. So in this case, suppression is justified and refers to a false positive case. Now coming to an unactionable example, in this code, the warning is actually valid. The exception class actually contains a non-serializable field, but developers explicitly stated that they don't intend the class to be serialized, so they suppress the warning intentionally, though the warning is valid. And here comes one technical data example. So the warning, that is URF unread public or protected field, is firstly suppressed, but later, in a later revision, developer replaced the directly exposed public fields with private final fields and accessor methods, and the previously hidden encapsulation defect was fixed later. So it refers to a technical data examples here. So to the best of our knowledge, there are no existing techniques for automatically classifying these suppressed warnings. And so developers still need to manually inspect the suppressions. This inspection often involve understanding the warning semantics, code context, developer justifications, comments, and they sometimes need to also go through the evaluation history. And prior work has studied warning suppressions, shown that suppressions are common, long-lived, and sometimes risky. And other LLM-related works, other works has also explored LLMs for static analysis related tasks such as warning interpretation for false positive reduction. However, existing work does not directly classify already suppressed warning based on their intent and maintenance impact, and this is the gap that our work addresses. So for our paper mainly makes three contributions. First of all, we construct a KAS bench, a benchmark of 680 suppression, manually annotated suppression instances from 9 Java projects. Second, we propose our approach, KAS-C. This is a knowledge augmented LLM-based framework for classifying suppressions. Thirdly, we evaluate KAS-C using ChatGPT, using GPT-5 Mini and Claude 4.6 Sonnet, and analyze where the knowledge augmentation helps and where the approach still struggles. So basically, we do a quantitative and the qualitative result analysis. So to evaluate the capability of LLMs in suppression classification, a dedicated benchmark is required. However, to the best of our knowledge, no such benchmark currently exists. That's why we curated our own benchmark, KAS-Bench. So we first selected nine Java projects which have enough suppression instances. Secondly, we mine the commit histories of the selected projects to extract suppression additions and removals, and we validated the extracted instances if the extracted code are complete and correct, and then we linked the additions, extracted additions and removals to reconstruct the suppression evaluation history. And after that, we performed a stratified sampling of representative cases for manually annotating the suppression instances. So we got 680 suppression instance, which we have manually annotated into 3 categories. So here is our annotation process. The annotation process was manual and carefully controlled. 2 authors independently labeled the instances, and these labels were based on the code snippets, the warning types, the developer's comments or justifications, Java doc of the code. There were commit messages, and we also considered the suppression evaluations, if a suppression is later removed or it is still remain in the code base or not. And We solved our disagreements through discussion, and we found that the Cohen's kappa score was 0.87, which is at almost perfect level. So here, so our final benchmark contains a total of 680 labeled instances, including 24 spot bugs warning types, and there are 104 false positive cases, 496 unactionable cases, and 80 technical dead cases. Now coming to our approach, that is KAS-C. This is the overview of KAS-C. First of all, we use a temporal split of January 2021 on our labeled benchmark. We got 437 instances that were added before the cutoff date, and we use this for our knowledge base construction. The other 243 post cutoff instances are used for evaluation of KAS-C. This is a two-step, and our KAS-C is a two-step prompting strategy. So in the first step, it takes a suppression instance as input and ask the LLM to classify the suppression using only the local code context and the category definition. And then and in the second step, it retrieves the knowledge base from knowledge from the knowledge base using the lookup key of warning type, and then ask the model to reconsider the same instance using that additional knowledge. And the final output includes the predicted category, the reasoning, and suggested action, such as if a warning should be fixed or suppressed. So for our approach, the knowledge base is a key component. It provides structured warning specific information for each of the 24 warning types in our benchmark. The knowledge comes from the pre-cutoff examples in our dataset, official spot bugs, Java or Oracle documentation. We have analyzed the GitHub issues and also went through Stack Overflow, Stack Exchange, and Reddit discussions to find out the common false positive and common unactionable cases which developers commonly face. And lastly, we have used LLM to summarize all the result and reviewed it manually to see that if those are consistent with the exact developers discussions or the examples. So our knowledge base is structured per warning type, and this is the schema of the knowledge base. We can see one example how an entry from the knowledge base look like. So yeah, this is an example entry from the knowledge base for URF unread public or protected field. So here the warning refers that a public or protected field is never read but declared. So one common false positive case is that field is actually used by one subclass or external test code, but the spot box cannot detect the cross-class uses. So this is and this field is not explicitly read in the class, but JUnit accesses it through access it reflectively at runtime. And next, one unactionable case that field sometimes some fields are intentionally kept for debugging or diagnostics, or it's accessed through external systems like JSON, JS, or even on the front end. So developers often suppress this warning because these are false positive and unactionable. And the source, and we have also included the source for these patterns. Next, we will look in the evaluation setup. So for evaluation, we used a temporal split to avoid data leakage. Suppressions before January 2021 were used to construct the knowledge base, and the suppressions added after January 2021, the post cutoff instances are used for the evaluation, and we use three models: GPT-5, GPT-5 Mini, and Claude 4.6 Sonnet for our evaluation. To perform an ablation study, we evaluated our vanilla LLM setting, where we used only the local code context and the category definitions. And in the full KAS-C setting, we have uh, we uh, pro- we provide the warning specific knowledge along with the local context, and we have compared these two setting for our evaluation. Mhm. So, to guide our study, we address the following research questions. For RQ1, we evaluated the full KAS-C setting to measure the performance of our approach. For RQ2, we measured the effectiveness of the knowledge base in KAS-C for suppression classification to improve the vanilla LLM-based classification. And for RQ3, we performed error analysis to find out in what situation LLM-based approach is struggle. So we will look into the RQ1 at first. So the uh, from the result, you can see that uh, for uh, for all of the models, we have achieved good results. For accuracy, Claude Sonnet got the best. 84%. Even for precision and recall, actually Claude performed the best. So the result shows that KAS-C achieves strong performance across all models, with Claude Sonnet achieving the best overall performance. Now we will look into the category level results. KAS-C actually performs well on unactionable suppressions because the knowledge base helps identify design decisions and external guarantees. The precision was above 93% for all of the models, and recall was also 81%. And but the hardest category for it is technical debt. Though the recall is high, 78 to 86%, the precision is a bit lower for only 49 to 66%. The problem is that technical debt is often confused with unactionable cases because both actually refer to valid warnings. So sometimes LLM cannot distinguish that if a valid warning is intentionally accepted, or if there are any external guarantees or framework guarantees. Now moving to the RQ2. So we have compared the performance of the vanilla LLM setting and the full KAS-C setting. The gray bars are for vanilla LLM setting, and the colorful bars are for the KAS-C setting. So from all of this, we can see that for every case, the KAS-C perform better compared to the vanilla LLM setting, which only uses the local code context. Then the largest improvement here is also for Claude with accuracy gain of 20.2% and precision gain 16.1 and recall 14.4. Mhm. Yeah. And so we can see that where the knowledge, like for which warning types the knowledge base help most. So the knowledge base helps the model corrects the cases that requires context beyond the visible code snippet. There is one warning, that is EI expose rep 2. For this warning type, the difference maker was the intentional reference sharing in builders wrappers or some project objects. And for NP null related warnings, there were the LLM could understand that there is framework null guarantees and some fail first checks from the knowledge base. And for URF unread public field, LLM could understand that there are some cases where some fields are accessed through reflection, test, JSON, or external framework uses. And also for the SQL non-constant string. There were cases where LLM could trust the internal schema generation and understand that which are the technical dead case and which are the unactionable cases. So here is one example of improvement from vanilla LLM to KAS-C. So in this code, the vanilla LLM output labels are dynamically constructed creatively statement at technical date. But after providing the warning specific knowledge, KAS-C could recognize it as trusted schema generation logic. Like this create table is only for generating the schema, but vanilla LLM could not understand that it's only for schema generation and not a real technical data. So this improvement example shows that how warning specific knowledge helps avoid over-interpreting safe project specific patterns. And now the research question 3. So for our research question 3, we perform the error analysis actually to see that to find out the regression cases and find out the cases that remained, find out the error cases that happen under both vanilla LLM and KAS-C setting. So, for GPT-5 Claude and GPT-5 Mini, for 3 of them, the regression case is only 5, 1, and 9. That means only 5 cases were correctly predicted by the vanilla LLM, but the KAS-C incorrectly classified those 5 cases. And whereas the improvement was 33. Like vanilla LLM could not correctly classify those cases, but the vanilla LLM improved those cases by correctly classifying those. And for GPT-5 Mini, there is only 1 regression case, and for Claude 9 regression case, whereas for Claude, in compared to the 9 regression cases, 58 cases actually improved. And now we have analyzed the common failure reasons. The common failure reasons include like over reliance on retrieve knowledge-based patterns. That means that when we provide the warning specific knowledge, LLM try to match the knowledge specific pattern strictly with the actual code snippet. And next one is over literal interpretation of warning semantics. That means that LLM over relies on the warning definition uh, of the particular warning code, and there is this category boundary confusion, one of the most common reason, because LLMs cannot LLM get confused between the unactionable and technical dead cases because both refers to some valid warnings. And also there are some confusion between false positive and unactionable cases as well. And there is insufficient snippet context. That means that the local code context that we are giving to the LLM does not provide enough context, like there is no justification or comments or any inline patterns. And there is also mismatch between retrieved knowledge and actual code. That means that uh, in this case, some part of the snippet matches with the knowledge base, but there are still like the context does not match exactly. And lastly, LLM sometimes make assumptions that is not supported by the snippets. Basically, LLM hallucinates some cases. And this is the common failure reasons for our KAS-C approach. And the key takeaways are that we have found out that for suppressed warning classification, only giving the local code context is often insufficient. And that's why when we provide the warning specific knowledge, it improves the LLM classification because it helps the LLM to understand the common false positive and common unactionable pattern. And overall, our approach improves accuracy across all evaluated models in compared to vanilla LLM setting. And we have found out that technical debt remains the most challenging category because it's often confused with unactionable. So thank you so much, everyone. Yeah, if you have any question, I'm most welcome.
Thank you very much, Rifah. Great presentation.
Thank you.
Amazing work by both of our speakers today. And we're almost at the end, but if anyone has any questions for either Rifah or Chaima, please feel free to raise your hand and ask your question.
Maybe I'll get us kickstarted because probably people will put up their hands soon. Rifa, just a quick question. So
Yes.
you assume that something is technical debt if
Yes.
it's not, let's say, relevant, or why do you assume that it's technical debt? Because it could just be a warning and not technical debt.
If there are some warnings that are not addressed initially, it can actually contribute to technical debt while it persists in the code base, and in future it can cause um, encapsulation issues, or there can be also security vulnerabilities. In case of SQL related cases, there can be risk of SQL injection or something cases. That's why.
Yeah, so it can be, but I think you're sort of assuming, and correct me if I'm wrong, maybe I didn't understand fully, right? You're assuming that they're all technical debt. Like some of them can be, let's say just an error, just a warning because you forgot to, I don't know, initialize a variable or whatever, right?
Yes, yes.
So, like, I don't know if I would consider that technical debt, but I'm assuming that, at least from you, what I saw, you're assuming everything is technical debt. So I'm just wondering, like, was there a further filtering or something, or is there a reason
You
why
mean
you
that if some errors are like just small errors,
Yeah, exactly.
no, yeah, here we are actually considering all the errors as technical errors, not
Okay.
just the major issues, also the minor ones.
Yeah, I think this is minor anyway, like to consider, but I just wanted to get a clarification. You might want to just refine that or think about it a bit deeper or whatever. But
Okay,
thanks.
thank you so much.
Anchor, please go ahead.
I have a question for Shaima. So in the limitation, you said that the baseline comparison is a bit tricky due to the human in the loop approach, right? Can you hear me?
Yes, I'm sorry, say that again. I feel the
Uh,
voice is a bit
so,
distant.
so in the limitation, you said that the baseline comparison is a bit tricky because of the human in the loop approach, right? Like compared to ChatDev and MetaGPT.
No. I think it's a bit tricky on the part of human in the loop, but in our evaluations, the human in the loop, we made sure that the human in the loop part or component did not influence any of the results.
Okay,
So, yes,
so all the 710 tests that passed were all like optimized plans. Like there was no human intervention where like the developer had to say, okay, this is not the plan that is like the most optimal, and then the worker or the main agent had to like reevaluate and then create like new plans.
yes, thank you for these questions. No, all the 700 tests, the unit test and the acceptance test have been passing as a one shot to the system, and there
Okay.
was not intervention of the human there. But in the first benchmark, because it was a mini games and a more like controllable tasks, we had the human observing all the planning there. So there was
Okay.
not an interactions of the human trying to change that, no, this plan is correct or not. All the tests have been passing with no interactions of anyone.
Okay. I have another question. So, like
Yes,
the architecture that you have, like there's a main agent and then there's a worker agent, and then you also
yes.
said that in the weakness that current agents have is that they do not have file access or they do not reference those files. Is like am I correct or did you say
Uh,
something else? Like I can't recall properly, but um, like in the weakness you said something about file or configuration files that like the current agents do not have, like do not reference those files or do not have access to those files when they create like a software from scratch, and then your
um,
does that because your memory has like all the configuration files and files that are required as well. Is
okay.
that
So if I understand the question correctly, if I am mentioning any limitation that the agent do not have access to. I think no, I think my limitations highlighted that we are saying that the evaluations, we have a hybrid evaluations with the baselines. So we have run two baselines, and the other two baselines, we did not run them. We had the results from their papers. So that's one of the limitations
Oh,
that
I'm
I'm
sorry.
saying.
I'm sorry. I wasn't talking about the limitations of your agent. Sorry to cut you off, but like I wasn't talking,
Okay,
but like
yes,
limitations of like the agents that you're comparing it with, like so ChatDev, Meta
yes.
GPT. So that was one of the limitations, right? That they do not have access to the files or like the configuration files.
They don't
Or
have access to a sandbox. That's if that's what
okay,
yes.
never mind.
So what happened to them is that they don't have a sandbox or any environment to run the commands. So they only like write the files and they
Mhm.
put the files and they said, okay, this is functional programs and it should be validated what the user asks. But do they run that file? Do they do a lint or any execution on that? They do not do that. And it's because they lack any components that catch the executions. So I'm saying that which is the third failure modes or limitations in the prior systems is that they don't have a grounding execution grounding.
Okay. Thank you so much.
Thank you. I think I saw another question.
I saw, yeah, Lucas, please go ahead.
Yeah. I have a question about the benchmarks that you used. I didn't have the opportunity to work with this benchmark yet. So my question is that the problems that you test your tool have front end, like it's a full stack problem or just a back end problem? And if it's a full stack problem, if you deal with like how can I be sure that the solution is working, but it's really working? Because sometimes when you use multi agents, the agents mock some data in the. So how you deal with that?
Yes. Okay, thank you, Lucas. So we have that's why we have like different benchmarks that grow in complexity. So the first one, they also cover the front end and the back end. So it's full stack. And we saw that it is not an assumed correctness, but a real correctness because we have ground truth tests that the agent run on that. So once we have the results of the pass rate on the tests, we see that, for example, if it's a mini game, we have a URL that is provided in our UI that have been executed in the sandbox. They said, I don't know, like Python, run these files, and or even we had a portfolio for junior, and the system have run it correctly, like have built it correctly, and we have the URL locally to access that website and navigate through different three different like components or trees of the web. So we try to catch if it's correct, if it's working into two dimensions with the tests, with that, and with the human seed and execution, and looking into like the generated projects and portfolios.
Yeah, but just the first data set, the easiest one, have front end. The other one don't have front end.
They have, yes, the first one is the one that have 20. We try to kind of have a balance because the first one have 20 tasks, the second one have 10, and the third one have 18. But they are more of more data scientist projects or even construction libraries from scratch. So we try to have, okay, front end, full stack, we have covered that. Now we want to see if it go in more complexity way to interact with, for example, machine learning project, then when we have a lot of dependency and especially the versioning of these libraries. So that was also one of the dimension to see difference.
Okay, thank you.
Thank you.
Okay, thank you very much, everybody. I'd like to once again thank both Chaima and Rifah for amazing presentations. And thank you to everybody for joining. The next trainee talks will be probably in June with a couple, two new students. So with that, thank you everyone and have a
Thank
great
you.
rest of your day.
Thank you.
Thank you.
Bye.
Bye.
Thank you. Bye.
Bye.